assume the switch is closed. Now we're going to open up that switch, and then we're going to recalculate out what happens to my test points. So your first thing is going to be, so we know that we got an open. What do we say about an open? What do we measure across an open? What's that?
Your source voltage.
Our source voltage. We're going to get our source voltage. So this switch is going to take all the source voltage. This thing's going to have a voltage drop across it of 12 volts. It's going to be my source voltage. So then what's going to be remaining voltages across all the other resistors then? Zero. All those are going to be up to zero because the switch took all the voltage. So all these are going to be at 0 volts now. Okay? So now, all we have to do is now we just have to identify what our test points are going to be. So what am I going to get from test point A?
12 volts.
A positive 12 volts. So don't keep your polarities. It's going to be a positive 12 volts now. It still is. Was and still is. Okay, then how about at test point B, what am I going to get? Zero. Because if I add up all my voltage drops, I'm going to get 0 volts. So I got to make sure I get my polarities in there, so it should be plus or minus 0 volts. How about at test point C? Zero. Test point D? Zero. And E? Plus or minus 0. Polarities. Okay, so polarities on all test points. Nothing on voltage drops. Alright, so that takes care of our first one there. Okay? So as long as I'm measuring across an open, if I go from here, I'm still measuring across my open, so I'm going to get all my source voltage. At test point B, I'm not measuring across my open, and there's no voltages left across the rest of those resistors, so those are all going to be all at 0. All right, so now we're going to close our switch back. Close our switch. And then we're going to open up R1. So R1 is going to be opened up. We're just going to, you can just kind of go and say, oh, it's gone, or just put an X through there. So now when I'm looking at it now, we know that R1's open. So what's the voltage drop across R1 going to be? What's that? You heard it. Yep, by 12 volts. It's going to drop my source voltage again. So what's my voltage across R2, R3, 4, 5, and 6? Those are all going to be 0. Okay? So now, I have all my voltage drops. And what am I going to get at test point A? Well, plus 12 volts, make sure you're using polarities. How about test point B? Plus 12. Plus 12. And I'm just going through the switch. The switch acts like a short. So that's going to be the same, just like if I had a piece of wire. So it's just kind of tying A and B together. Okay, then how about at test point C, what am I going to get?
0.
Plus or minus 0. Test point D?
0.
Plus or minus 0. And E?
0.
All right. Okay, so we're always looking at, what do I measure across an open, what do I measure across a short? All right, then our next one is open R2. We're going to draw R1 back in there. If you're on your schematics and stuff, you can just go ahead and draw, just draw your fault in there so you know what it is. So R2 is open. What's that one going to drop for voltage?
9 volts.
12 volts. Okay, how about R1? What's that one going to drop?
12 volts.
Okay, so if R2 is dropping all the voltage, how much is left across all the other resistors?
0.
0. So R1 is going to drop 0 volts. How much voltage is going to be dropped across R3? 0. So all those are going to be dropping 0 because R2 took all the voltage.
Those A and B would have still be 12.
So A and B are still going to be at a positive 12 volts. Still measuring my source voltage. And I am still measuring across my open. So if I were to bring my red lead down to my black lead, put my black lead on ground, never move it, bring my red down. If I do it, I go down and I come down and I know that my switch is going to drop 0 volts. So I got plus 0, R1 is dropping 0 volts, I got another plus 0, R2 is dropping all the voltage, so now I got plus 12 volts. And if I keep on coming down, I got plus 0 volts, so I'm going to end up with my 12 volts. So either measuring across A or B, I'm still measuring across my open. I'm going through the whole circuit, but I'm still measuring across the open. Same thing with test point B, I'm still measuring across the open. Come down to C, what am I going to measure for voltage? Plus 12 volts, because I'm still measuring across my open. How about at test point D now? 0. And we know that D and E are the same, so we're just going to fill those in right away. We don't even need to analyze that one. We know those are the same points. Okay? All right, any questions on that one? Catching on? All right. We're going to remove our errors, our voltages. We're going to insert it back into a working order. There we go. Okay, now our next one then is a shorted R3. So that would be just like having a piece of wire right going across R3. It's shorted out. So R3 has a short, and if I was to measure the voltage drop across R3, what would I measure for voltage across R3 now?
0 volts.
0 volts. What would I measure for voltage across R4?
0 volts.
0 volts, because what remains constant in parallel circuit?
Voltage.
My voltage. So if R3 is 0 volts, that means everything else in that parallel circuit has to be at 0 volts. Okay? So now what's my voltage drop going to be across R1 and R2? So with our R3 shorted out, our equivalent circuit is going to look like this now. So sometimes it helps to draw in your equivalent circuit. So here's R1. Here's R2, and then since R3 is shorted out, it's not even part of the circuit anymore. It's just shorted out, it's not even part of the circuit. So now here's our new equivalent circuit for this circuit. R1 is 3.3 ohms, and R2 is 4.7 ohms. Okay, so now what type of circuit do I have? Series. What's another name for a series circuit? Voltage divider. So remember, we're not doing anything with currents, so we don't need to recalculate out current. So what would be the formula that I could use for figuring out what the new voltage drops across R1 and R2 are? Use our voltage divider formula. So figure out what the voltage across R1 is.
4.95 volts.
So we got VR1 is equal to R1 over our new RT. You know, by adding up those, you get what? How many?
8 ohms.
8 ohms. And then you're going to multiply that by my voltage source of 12 volts. Okay. So, and then what did you say, Mike, you got for voltage across R1?
4.95, and the second one was 7.05.
Okay, 4.95
95, sorry.
volts. And then the R2 then is just going to drop the remainder. So if I just take 12 volts divided, or take 12 volts and minus this voltage, I'll get the remainder amount of voltage. And what's my voltage of that one?
7.05.
7.05 volts. And if I add those two up, if I add up those two voltages, I should get my 12 volts again. Okay? So I changed the circuit up. Changed up to mean R1 and R2 now had to take up the voltages that R3, 4, 5, and 6 aren't taking. So they had to absorb some of that, some of those voltages. So R1 now is okay, so there's our new voltage drop across our original circuit. So now what am I going to measure at test point A then?
12 volts.
So measure my first voltage. And my test point B, what's that? 12 volts, and plus 12 volts. Still measuring my source voltage. Or the sum of all my voltage drops. And then at test point C, what am I going to get?
I'll say 7.05 volts.
7.05 volts. Good. And then across test point D and E?
0.
0. Okay, so when something happens to our circuit, the other components have to make up for the difference of it so that it always equals up to my source voltage. So some of these voltages are going to change and, accordingly to take up the voltages that got lost from the other components that went bad on us. So now did our IT increase or decrease in resistance or in current? What happened to my IT once the R3 got shorted out? Did it increase, decrease, or stay the same? How many people say it stayed the same? How many say that it increased?
With an open and decrease.
Be an increase. 1.5 amps,
Yeah, it increased. Because what happened to our total resistance was only, what, 8 ohms did you say it was?
yeah. Yeah, decrease.
Yeah, so our total resistance was only 8 ohms now. We used to have 56.49 ohms. So our T went down, so our resistance went down. That means our total current had to go up. So now we're drawing a lot of current off the circuit. It went from 212.4 milliamps, so what did you say it was?
It was 1.5 amps.
So now it's up to 1.5 amps. So yeah, our current went way up there. These ones that are all in parallel, these are typically what are going to be our loads. Everything else is just our voltage dividers to get up the voltages that we need. So what it does is it just protects our circuit so that if any one of our loads happens to get shorted out, we're not burning up our fuses or we're not burning up our power supplies. And what we call these are just our current limiters. Maximum amount of current I can get going through there if one of my loads shorts out is going to be 1.5 amps. So I could have this thing fused at 1.5 amps, and if anything shorts out, I'm not going to be blowing fuses all the time. It's not going to hurt my power supply and stuff like that. So what we call these ones here are current limiters. These two resistors that are just in series are what we call our current limiters. You can either have one or two resistors in series depending on what we want for wattages and what we want to have. Especially if we want to come out from another output, you know, at 11.3 volts, we might want to have that two resistors in there, but those are our current limiters in there. So we never, so even if our loads directly short out, we're not putting a short across our total power supply. All right, any questions on that one? Okay. All right, next one then is going to be our open R4. So we're just going to remove R4 from our circuit. Okay? So now what's going to happen to my circuit? So again, sometimes it works to redraw up your schematic so you can see what's going on. Now I only have 3 resistors in my parallel circuit because R4 is not even in there anymore. So if I remove one of my circuits from my parallel circuit, what's going to happen to my total resistance of that parallel circuit? Is it going to increase, decrease, or stay the same?
Increase.
Yeah, it's going to increase. That resistance of that parallel circuit is going to increase. So if this resistance of this parallel circuit increases, what's that voltage across the parallel circuit going to do?
Increase.
It's also going to increase. So what did my resistance for this parallel circuit increase to? What's my new parallel circuits for R2, 3, and 6? Let's see, R3, R5, and R6. What's our new parallel resistance for that new parallel circuit now? 66 point. 36?
37.
37?
Yeah.
Oh.
Forgot to remember it.
Okay. So now we just kind of made that all into one resistor, right? Now we still have R1, R2, R3 is 3.3 ohms, R2 is 4.7 ohms. We just made ourselves an equivalent resistor, so now we have ourselves a series circuit. Now we can just go ahead and use our voltage divider formula again. So come up with your total resistance and divide up your voltages amongst those 3 resistors. So then, so do that and then figure out what you get for voltage across R1, R2, and the combination of R3, 5, and 6 now. Start getting your voltages, let me know and I'll write them in there.
10.7 on the parallels.
Okay, so you got 10.7 volts across the parallels. Okay, good. Okay, 758.4 millivolts across R2. Okay, everyone agree with that? All right, and how about R1? 532.5 millivolts across R1. If I add all those up, if I come down one particular row, do I end up equaling with 12 volts? All right. Okay, so everybody agree with it then? All right. So now what's going to be my voltage at test point A then? Plus 12 volts, don't forget your polarities. We're going to use plus and minus voltages. Okay, how about test point B? What is it?
Plus 12 volts.
Plus 12 volts. Okay, and then how about test point C? Well, guys, so bring your red lead down to your black lead. Here's test point C, right? So first sign I got is a positive 758.4 millivolts plus 10.7 volts gives me what?
11.47 volts.
Positive 11.47 volts. Okay. Then how about from DV? How much?
Plus 10.7.
Yeah, plus our 10.7 volts. And then it would be the same thing. Okay? So watch out what happens when something changes. So once this resistance changed, the resistance of this parallel circuit went up, it had to take more of the voltage. So I took away the voltage from R1 and R2 and gave it to its parallel circuit. So that voltage across that parallel circuit ended up going up from 10.3 to 10.7 volts. All right, any questions on that one? All right. We'll put our 4 back in there. And then we're going to short out our switch. The switch is shorted out, so no matter what I do with that toggle, if I turn on and off that switch, my circuit's always going to stay on. So what am I going to get now for, so what's going to happen to my voltages across R1, R2, and R3, 4, and 5, and 6? What's going to happen? What's that? What will happen to my voltages across R1, 2? Yeah, nothing's going to happen, right?
But when you say shorted, you're always going to state that it just bypasses that one component?
Yep. So no matter even if I open up that switch, I still have a short on it, right? So that circuit's still going to be powered up. It's just like my switch just isn't going to work. It's just a short going across it. So I'm going to just get my, it's just a non-functioning switch, but yet all the voltages are all going to stay the same to our original voltages. So what's going to be my voltage at test point A then?
12 volts.
No?
That's still be 12.
That's still going to be 12. Okay, then how about test point B? No?
12.
So what do we have for our original ones? We had what? Right, test point B for our original
12
circuit.
volts.
We had our plus 12 volts. What was my original voltage for test point C?
11.30.
That stayed at 11.30. All stays the same, and then at test point DDE?
10.30 volts.
Plus 10.30 volts. Yep, it doesn't really change anything, it's just that I can't turn my circuit off. Okay, my switch just isn't functioning properly. Okay, so a short, a closed switch is just like a short, except it's functioning. So I can turn my circuit on and off. But if I short out my switch, then it's just my switch is shorted out and it just isn't functioning anymore and I can't turn it on and off, but everything else stays the same. Alright, last one here. Alright, start to test point C to ground. So basically I'm going to just take go from test point C, and then we go right down to ground. Okay? So what am I gonna measure across? What are going to be some of my voltage drops across some of my components going to be? What's going to be the voltage across R1?
12 volts.
12 volts. Okay, and if you don't see that, if I have a short from test point C to ground, if I put my red lead on here and I'm going to measure, what am I going to measure for voltage at test point C?
0 volts.
0 volts. So if I wanted to bring my red lead down to my black lead, I need to make sure I end up equaling 0 volts. So that means that when I come down, if I go across R2, there can't be any voltage across R2, right? So that's got to be plus 0 volts. Come down to R4, plus 0 volts. So all these components here must be dropping 0 volts because the short is going across all those components. You measure across the short, so there's no voltage across those. That's just like having, so my equivalent circuit now would look basically just like this. All I have in there is that one resistor. Everything else is shorted out. So R1 is going to take the 12 volts. Lot of current. Oh yeah, a lot of current. Oh, the switch is open. Oh. Right. There we go. Now we got current going through there. Now we got a lot of current going through there.
That resistor's not going to last long.
Oh, well, Dan, what we rated at.
Yeah.
Yep, if we have it, if it's our current limiter, we're going to make sure that that resistor is rated at the wattage. So if something happened to our test point C and that did short out, we're going to make sure that that has a big enough resistor in there that'll.
Could you have really minute resistance values that have massive power distribution values?
Oh yeah, we can go, remember, it's not anything to do with the value of the resistor, it's the size of the resistor. So I could have a 1 ohm resistor that's this big, or I could have a 1 ohm resistor that's only this big. It all depends on how much power we have to make sure we dissipate from it. But the size of the resistor has nothing to do with the value of it. So.
Just the power distribution.
Yep, just how much of that power gets dissipated. Alright, so what am I going to measure at test point E then?
12
Plus
volts.
12 volts.
Plus 12 volts. Still going to measure my source voltage. How about test point B?
Plus 12.
Also plus 12 volts. Test point C? 0. Plus or minus 0 volts. It's shorted out to ground. And we'll get the same thing here. Alright? Alright, so that's our first one. Alright, any questions on our first troubleshooting one? Alright. Let's take a look at the second one. What's that?
That's really hot.
Yeah, it's cooking. He's got a lot of current. Yeah.
So 5 watt resistor will work on it, right?
Let's figure out what size value would I need for R1, or what size resistor value what size wattage resistor would I need for R1? That's a good question. So what size wattage resistor would I have to put in there?
Formula for that?
So what size power resistor, what size resistor would I need in there? What wattage resistor would I need in there?
50 milliwatts.
Yeah, so we need at least a minimum 50 watt resistor in there. So that thing's gonna be big. So that's
Breakers?
hold on, wait here.
I just got blown my nose.
So yeah, it would be, so we could have a 3.3 ohm resistor that's the same size that's in your parts kit, or we could have a 3.3 at 50 watts. That would be something very similar to this. I think this is actually probably closer, might be closer to 100 watt.
But that's worth the resistance value.
This one here, but it could be a 3.3.
Plug it in and find out.
For all practical purposes, I'll just say this is a 3.3 resistors. Yeah. Yep, so you would need something that big. All the other ones, all these ones could be just our little 1/8 watt ones. So this one right here would have to be a real big one.
So a parallel group of resistors acts as a voltage divider altogether,
Current divider parallel.
but altogether they would act as a voltage divider, like a
No.
series resistor.
No, not a voltage divider.
They drop it to 10.
Yeah, they all drop 10.3 volts, so they're never going to divide up the voltage, they only divide up the current. But the sums of all these powers would be additive. For you? Yeah, but it's not a voltage divider. Yep. All right, so before you go and take a break, and if you want to stick around and start working on worksheet number 2 here, here's what your it's going to look like on your final. But you should be able to know how to straight line. So I'm going to have you start working on the straight line. You can take a break, but then start working on the straight lining of this circuit here. When you get back from break, start straight lining that one. Work with others and stuff. Make sure you know how that what straight line. If you think you got it, call me over and I'll tell you if you got your straight line correct or not. So, all right.